So this video is the multiple choice questions for the AP Physics exam for the topic of fluid mechanics. And it can also be used as practice for the IB and GCSE exams. So for question 1, a large tank is filled with water to a depth of 6 meters. If point X is 1 meter from the bottom and point Y is 2 meters from the bottom, how does Px, which is the hydrostatic pressure due to the water at point X, compare to Py, the hydrostatic pressure due to the water at point Y? So because X is 1 meter from the bottom, it is 5 meters from the surface of the water. And the hydrostatic pressure at point X is equal to rho g times hx, where rho is the density of water, g is the gravitational acceleration, and hx is the depth, equal to rho g times 5 meters. And in the same way, the hydrostatic pressure at point Y is equal to rho g times hy, equal to rho g times 4 meters, because Y is 2 meters from the bottom. So we want to find how Px compared to Py, so we divide Px by Py equal to 5 over 4, or 4Px equal 5Py, and the answer is D. So for question 2, in the figure above, a box of dimensions x, y, and z rests on the bottom of a tank filled to a depth of d, with a liquid of density ρ. If the tank is open to the atmosphere, what is the force on the shaded top of the box? So because the top of the box is at a depth of d minus z below the surface of the liquid, the pressure on the top of the box is equal to P atmosphere plus rho g times h, equal to P atmosphere plus rho g times d minus z. The area of the top of the box is equal to xy, and so the force on the top of the box is equal to Pa, equal to P atmosphere plus rho g times d minus z times xy. And the answer is C. So for question 3, the figure above shows a closed container partially filled with liquid. Point Y is at a depth of 1 meter, and point Z is at a depth of 3 meters. If the absolute pressure at Y is 13,000 Pascal and the absolute pressure at Z is 29,000 Pascal, what is the pressure at the surface, which is point X? So let P naught be the pressure of the gas at the surface of the liquid, which is at point X. Then the pressures at points Y and Z are given by Py equal P naught plus rho g times 1 meter, and Pz is equal to P naught plus rho g times 3 meters. If we subtract Py from Pz, we get rho g times 2 meters. And because the values of Py and Pz are known, this is equal to 16,000 Pascal. So from this we have rho g is equal to 8,000 Pascal per meter. So we want to find the pressure at point X, and we know rho g and Py. So P naught is equal to Py minus rho g times 1 meter, equal to 13,000 Pascal minus 8,000 Pascal per meter times 1 meter. And this gives 5,000 Pascal. And the answer is C. So for question 4, a plastic cube 0.5 meter on each side and with a mass of 100 kg floats in water. What fraction of the cube's volume is above the surface of the water? So the density of the plastic cube is equal to its mass over its volume, equal to its mass over the length of the side cube, equal to 100 kg over half meter cube, equal to 800 kg per meter cube. So for an object partially submerged in water, the buoyant force is equal to the weight of the object. The buoyant force is equal to the density of the fluid times the gravitational acceleration times the volume of the displaced fluid. And the weight of the object is equal to its density times the gravitational acceleration times the volume of the object. V displaced over V object is equal to rho object over rho fluid, equal to 800 kg per meter cube over 1000 kg per meter cube, equal to 4 over 5. So the volume of the displaced fluid is equal to the volume of the cube that is submerged in water. So the fraction of the cube submerged is 4 over 5. And this means that 1 over 5 of the cube's volume is above the surface of the water. And so the answer is A. So for question 5, a block of styrofoam with a density of rho s and volume v is pushed completely beneath the surface of a liquid whose density is rho l and released from rest. Given that rho l is larger than rho s, so the liquid density is larger than the density of the block, which of the following expressions gives the magnitude of the block's initial upward acceleration? So the buoyant force on the styrofoam block is equal to rho L times V times G. And the weight of the block is equal to ms times g equal to rho s v times g. Because rho L is greater than rho s, then the net force on the block is upwards and has the magnitude equal to B minus weight equal to rho L minus rho s times v times g. And by Newton's second law, the acceleration of the block is equal to the net force over its mass equal to rho L minus rho s times vg over the density of the block times its volume equal to rho L over rho s minus 1 times g. And so the answer is B. So for question 6, in the figure above, a ball of specific gravity 0.4 and volume of 5 times 10 to the minus 3 meter cube is attached to a string, the other end of which is fastened to the bottom of the tank. If the tank is filled with water, what is the tension in the string? So the buoyant force acting on the ball is equal to the density of water times the volume of the displaced fluid, which is equal to the volume of the ball times the gravitational acceleration equal to 1000 kilogram per meter cubes times 5 times 10 to the minus 3 meter cube times 10 meter per second square. And this gives the buoyant force equal to 50 newtons. The weight of the ball is equal to its density times the volume of the ball times the gravitational acceleration equal to 400 kilograms per meter cube times 5 times 10 to the minus 3 meter cube times 10 meter per second square equal to 20 newtons. So the upward force, which is the buoyant force, balances the total downward force, which is gravity plus the tension in the string. So the tension in the string is equal to the buoyant force minus the weight of the ball, equal to 50 newtons minus 20 newtons equal to 30 newtons. And the answer is B. So for question 7, an object of specific gravity 2 weighs 100 Newton less when it's weighed while completely submerged in water than when it's weighed in air. What is the actual weight of this object? So the buoyant force is equal to the density of water times the volume of the displaced fluid, which is here equal to the volume of the object, times the gravitational acceleration. If the object weighs 100 newtons less when completely submerged in water, then the buoyant force must be equal to 100 newtons. And so the volume of the object is equal to 100 newtons over the density of water times the gravitational acceleration, equal to 100 newtons over 1000 kilogram per meter cubed times 10 meter per second square, equal to 10 to the minus 2 meter cubed. So now that we know the volume of the object, we can find its weight. So its weight is equal to its mass times the gravitational acceleration equal to its density times its volume times g. So we can find its density from the specific gravity by multiplying it by 1000. So equal to 2000 kilograms per meter cube times 10 to the minus 2 meter cube times 10 meter per second square equal to 200 newtons. And so the answer is A. So for question 8, in the pipe shown above which carries water, the flow speed at point X is 6 meters per second. What is the flow speed at point Y? So this is the diameter of the pipe at point X and point Y. The cross-sectional diameter at Y is 3 times the cross-sectional diameter at X. This means that the cross-sectional area at Y is 3 to the power 2 equal to 9 times the cross-sectional area at X. So the continuity equation tells us that the flow speed V is inversely proportional to the cross-sectional area. So because the cross-sectional area at Y is 9 times the cross-sectional area at X, then Vy over Vx is equal to Ax over Ay equal to 1 over 9. So Vy is equal to Vx over 9 equal to 6 meter per second over 9. So it is equal to 2 over 3 meter per second. And the answer is A. So thank you for watching and see you in the next video.